Hi friends, my name is Mihir Patel. My student ID is 2022015006. I am from DAIICT. Our group is making a project on algorithms behind a Google Map. In this video, we will discuss about the basic idea behind Dijkstra's algorithm. Dijkstra's algorithm is greedy algorithm. So it follows the greedy algorithm technique. The basic idea behind this algorithm is at every node we have a cost to reach at that node from the source node. From the this node equal to node 1, we explore all nodes where we can reach directly from the this node 1, and if the new cost, which is equal to cost to reach source node to node 1 plus cost to reach node 1 to current node, is less than the previous cost of current node, then we update the cost for the current node. After, from the node 1, we choose minimum cost node and include this chosen node in a path. We repeat this process until all nodes are visited. The basic step which we are doing at every node is, if distance of v is the previous cost to reach at node v from the source node. And suppose we are currently standing on node u. From the node u, we can reach directly to the node v. So the new cost is distance of u plus length of uv. Then we check one condition. If distance of u plus length of u comma v is less than distance of v, then we update distance of v equal to distance of u plus length of u comma v. Thank you. Hope you enjoy this video. In the next video, we will see steps included in Dijkstra's algorithm.
Hello guys, before I start my discussion, I'll clarify that these videos are related to a discrete mathematics project, which is inspired by Professor Manish Kumar Gupta, Professor Manoj Rao, and Professor Prasenjit Kundu. And our team members' names and IDs are shown on the screen. First of all, I will introduce myself. I am Smith Fairfer and my student ID is 2022012553. So, in this video, I cover the steps included in the Dijkstra's algorithm. And what will I say in this video? I already wrote in these slides. So it is very easy to understand. So let's start. Dijkstra's algorithm is a popular graph traversal algorithm used to find the shortest path between a source node and all other nodes in a weighted graph. It is a basically greedy algorithm that gradually updating the shortest path distances from the starting node to each node. So how to use this algorithm, or what is the steps included in this algorithm, which are mentioned in the next slide. And in the graph, each edge has weight or cost associated with it, representing the distance between the connected nodes. In the initialization state, the distance value of the source node is set to 0, while all other nodes are set to infinite initially. Because initially we don't know the distances of all nodes from source node, so we assume that all the nodes are at infinite from the source node. And mark all nodes as unvisited. In second step, choose the closest node among the unvisited nodes. This node will be the current node for the iteration. In the third step, for the current node, consider all of its neighboring nodes that are still unvisited. Calculate the tentative cost from the source node to each neighboring node by summing up the distances from the current node to the neighbor. If the newly calculated distance is smaller than the current distance value of the neighbor, update the neighbor's distance value. In the fourth step, once all the neighbor nodes of current nodes are visited, then mark the current node as visited. A visited node will not be checked again. Repeat upper steps until the goal node will be visited. If the destination node is reached, the algorithm will terminate early. So at the final result, we get shortest path distance from source node to every other nodes. To understand these steps easily, look small example. Consider below graph to understand the steps which are used in this algorithm. Here in this example, we consider source node has first node. Distance from source node to source node is 0. And for other nodes, we don't determine the distances from source node. So we assume that distance of the nodes from source node will be infinite. For further process, we use steps which we learned in previous slides to solve this sum easily. Since we are choosing to start at node 1, we can mark this node as visited and add a star to the corresponding node in a graph. Now we need to start checking the distance from node 1 to its adjacent nodes. As you can see in the diagram that these are the nodes 2 and 3. We need to update the distances from node 1 to node 2 and 3 with the weights of the edges that connect them to node 1, and these weights are 5 and 6 respectively. After updating the distances of the adjacent nodes, we need to select the node that is closest of the current known distances. Mark it as visited. Add it to the path. From the diagram, we can see that the node 2 is closest to source node. So we add it to the path. See the new updated graph. We make a star at a node which is already visited and draw a red line on edge which is included in our path. Now we need to analyze the new adjacent nodes to find the shortest path to reach them. We will only analyze the nodes that are adjacent to the nodes that are already part of the shortest path. So the nodes 3 and 4 are the nodes that we will analyze in the next step. Update the distance from the source node to the new adjacent node. Distance of node 3 we already add to the list. For node 4, the distance is 15 because we have to add the weights of all edges that form the shortest path to that node. We have to choose which node will be added to the path. We must select the unvisited node with the shortest distance to the source node. So we find the node from graph that is the node is 3. We add it to our path and do a star at that node. Now we need to repeat this process. Find the shortest path for all other nodes. So in our example, the last and adjacent node is 4. From path 1 to 4, the distance is 15. And from path 1 3 4, the distance is 14. So the shortest distance is 14. So add this path in our original shortest path, which are in red edges. So we finally get the shortest path from source node to all other nodes using the steps which are covered in previous slides. So the final graph and diagram is given below. So using upper steps, we are finding the shortest path between any two nodes in a graph. So these steps are very easy to solve any problem related to finding shortest path in a graph or map. So in this section, we see the steps included in Dijkstra's algorithm and related small example to understand how actually implement the steps in a problem. Here we only cover small example, but if you are curious to solve other big and unique problem, which is basically solved by these simple steps, then see our next video. Thanks for watching this video.
Hello guys, Namaskar. I am a student of DAIICT and currently we are working on a project in discrete mathematics inspired by our respected professors Professor Manish Kumar Gupta, Professor Manoj Raut and Professor Prosenjit Kundu. And this is our team. There are 6 members in our team. I am Disant Patel and my student ID is 2022 We have a topic in this project on algorithms behind Google Maps that you have learned in previous videos. And one thing before starting this video, I will strongly recommend that you watch the previous videos first and then watch this video. In this video, I am explaining an example of Dijkstra's algorithm. So let's start the example. Here the this source, this red one is our main source node, and all the others are goal node. As we already learned before that we will initialize the distance of the source node from itself to be 0, and the other node's distance from the source is to be infinite. And now we can go to the to second node, third node, and sixth node from this source node first. And we as we have learned before that if distance of u plus cost of u to v is less than distance of v. I am explaining this. Here u is our starting node and v is our approaching node. Distance of u means distance of that node from the source node, and this cost means how many how much value you have to spend to reach the approaching node. And if this condition satisfies, then we will update our distance of v equal to distance of u plus cost of u to v. This is this is called relaxation condition. Okay. So from this we can find our distance of the node 2, that is distance of u. Distance of source is 0 and the cost of source to the second node is 7. So distance of the second node will become 7. Distance of the third node is 0 plus 9 equal to 9. It will become 9, and the distance of 6 will become 14. And these all are less than infinite, so we have updated our value, and it is also called relaxed. We have relaxed these nodes. Now in these all values we will choose the minimum value, that is 7, and it means that this second node is visited, or we have found the minimum distance for it, and we will mark it red. Now we can go to the third node or fourth node from this second node, and we will find distance of fourth node. It is the distance. Now second node will become u and fourth node will become v. Now distance of the fourth node is distance of u, that is 7, and the cost of 2 to 4, it is 15. So distance of the fourth node will become 22, and similarly distance of third node via second node via this path will become 17. But this 17 is greater than this one that we have already get. So we will not updating the distance of third node. we will keep the distance at 9 only, and we will relax the fourth node distance that was initially infinite and now 22. This is all that I have told you. Now from the third node we can go to the fourth node or to the sixth node. The distance of the fourth node via this path is 9 plus 11. It is 20. That is less than the previous value, that was 22. So we will reduce this value and relax our fourth node to the value 20, and we can go to the sixth node via this path, and this cost is 11. That is also less than the previous value of the distance of sixth node. So we will also minimize that. We will choose the minimum value bit amongst these 11 and 20, that is 11, and we will mark the sixth node. Now from the sixth node we can only go to the fifth node, and through this path the distance of the fifth node will become 9 plus 2 plus 9, that is 20. We will update the 20 value in our table, and now you can see that the distance of 4 is also 20, and the distance of 5 fifth node is also 20. So in this case we can visit any of the node first and then second, and so we will visit the fourth node first and then fifth one. We will mark red for first and then fifth. And now we have got the minimum value for all the nodes. Yes, here one thing to tell, you can go fifth node via fourth node also, but this value is more than 20, that it will become 26. So we have not considered this path, and we have considered this path to reach to fifth node. It is optimal route, and we have completed our example. I hope you have understand this example very well. So that is all from my side. Thank you for watching this video. See you in the next video.
Hi friends, my name is Mihir Patel. My student ID is 2022015006. I am from DAIICT. Our group is making a project on algorithms behind Google Map. In this video, we will see about the correctness of Dijkstra's algorithm by induction method. We will prove that Dijkstra's algorithm is correct by induction. Capital G is the input graph, small s is the source vertex, L of UV is the length of an edge from U to V, and capital V is the set of vertices. The pseudocode for Dijkstra's algorithm is as follows. Let du of v be the label found by the algorithm, and let del of v be the shortest path distance from S to V. We want to show that du of v equal to del of v for every vertex v at the end of the algorithm, showing that the algorithm correctly computes the distances. We prove this by induction on modar via following lambda, where mod R is the number of the element in a set R. Lambda. For each x belongs to R, du x equal to del of x. Base case when mod are equal to 1. Since r only grows in size, the only time mod are equal to 1 is when r equal to source vertices and distance of source vertices equal to 0, which is equal to del of s, which is correct. Inductive hypothesis. Let U be the last vertex added to R and let R dash equal to R union U. Our inductive hypothesis is for each x belongs to R dash, d of x equal to del of x. Using this inductive hypothesis for every vertex in R dash that isn't U, we have the correct distance label. We need only show that du of u equal to del of u to complete this. Suppose for a contradiction, we assume a statement that the shortest path from S to U is a Q and has length L of Q. So for from this statement, L of Q is less than D of U. This is our inequality number 1. Q starts in R dash and some leaves R dash. To get U which is not in R dash, let xy be the first edge along Q that leaves R dash. In this statement, x in R dash, but y node is not in R dash. Let qx be the subpath S2 x of q. Clearly, we can say that length of qx plus length of xy is less than or equal to length of q because length of y to u we didn't add in this statement. So this quantity is must be less than or equal to length of q. But length of xy is positive or 0. So length of qx is less than or equal to length of q. This is our inequality number 2. Since d of x is the length of the shortest S to x path, by inductive hypothesis, it has the correct label. So, d of x is less than or equal to L of qx, giving us the inequality number 3. d of x plus length of xy is less than or equal to length of qx. Since y is adjacent to x, d of y must have been updated by the algorithm. So, d of y less than or equal to d of x plus length of xy. This is our inequality number 4. Finally, since U was picked up by algorithm, to bind the pseudocode, you must have the smallest distance label. So, d of u less than or equal to d of y. This is our inequality 5. From the inequality 4 and 5, if we combine this both inequality, we find that d of u is less than or equal to d of y is less than or equal to d of x plus L of xy. So d of u is less than or equal to d of x plus length of xy. This is our inequality number 6. From the inequality 6 and inequality 3, this is our inequality 6 and this is our inequality 3. So combining both, we find u of u is less than or equal to length of qx. This is our inequality 7. From the inequality 2 and inequality 7, this is our inequality 7 and this is our inequality 2. So on this inequality, d of u is less than or equal to length of q. This is our inequality number 8. From the inequality 1 and inequality 8, d of u is less than equal to length of q. This is our inequality 8. And length of q less than d of u. This is our inequality number 1. So d of u is less than d of u. But this is the wrong statement. So we get a contradiction. Therefore, there is a no such shorter path q exists. So d of u equal to del of u. This lemma shows that algorithm is correct by applying the lemma for r equal to v. Thank you. Hope you enjoy this video. In the next video, we will see the problems of Dijkstra's algorithm and its solution.
Hello guys, welcome to a new video. My name is Chintan Bara and I am from DAIICT and I am doing my project upon discrete mathematics. It is inspired by Manish Kumar Gupta, Professor Manoj Raut and Professor Prosenjit Kun. This is my ID and you already know about our project which is on algorithms of Google Maps. So let's get started with this. But before we get started, do check out the previous videos because if you don't watch them, you won't be able to understand what is happening or what's going on here. So let's get started. My topic is problems related to Dijkstra's algorithm. So basically, I'm trying to show that what kind of problems can occur on the practical ground in Dijkstra's algorithm. As you know, already know about Dijkstra's algorithm very much, I guess, from the previous videos. So a few problems can occur on the practical ground only. Theoretically, it's not much of a defective. So first one is inability to handle negative weights. In this algorithm, we assume that all edges are non-negative. If any of them were to be negative weighted, then the algorithm might consider it as a lower value and it might result in incorrect output. Next up is inefficient for large graph. This algorithm traverses through node and one node to another node. So you can understand that it has a time complexity of big O of v plus e times log v, where v is the number of vertices and e is the number of edges. Hence, if it traverses from node to node, then for larger graph, the it might get more inefficient. Next up is inability to handle disconnected graphs. If the graph is disconnected, meaning that if there is any vertices or nodes that are not reachable from the source node, let's say that certain nodes are not connected to each other through edges and that node only has the shortest path, then in that case the algorithm might produce an invalid short path. Up next is inability to handle graph with cycles. Now think of a graph that has four nodes connected to each other and one of the node is connected to source node and another node is connected to the destination. Now the source node which is connected to that cyclic loop of four nodes is has started traversing. Now the algorithm might get stuck into that four node which are connected cyclically because of the equal distances, or you can take any formation which results in equal edges, equal weight of the edges, and the algorithm might generate an incorrect output or it might get stuck into the loop for infinity. Such graphs are called DAGs. This is written here, directed acyclic graph. Okay, so next up is sensitivity to edge weights. Now Dijkstra's algorithm assumes that the edge weights are static and do not change during computation. If the edge weight change dynamically during the algorithm's execution, it might produce invalid result. So you already saw through example that weights cannot change uh, as per Dijkstra's algorithm, and if they change, which is think of a case scenario that you are traveling and you change your destination node from one place to another, then in that case the Dijkstra's algorithm might get confused with the destination node and result in an improper shortest path. Which might result in an improper shortest path. Up next is inefficient updates of priority. Now, Dijkstra's algorithm normally uses a priority queue to keep track of the nodes with their respected distances. And if you are a coder, you know about priority queue very much. But to give it a short, view of information, a priority queue is something that prioritizes certain things and certain values. So, Dijkstra's algorithm normally uses a priority queue to keep track of the distances, the shortest node path as well as the distances. And this priority queue, while updating, uses a lot of time as well as space. So, if the graph which we are traversing with is larger, much larger in fact, then it might get worse in that case because updating the priority queue is not an easy task. Now, to counteract some of the inefficiencies of Dijkstra algorithm, Bellman-Ford algorithm was introduced. There is also the A-star algorithm, which you might, if you want to understand, or you should understand by watching our videos, by watching next parts of our video. This is only just a little discussion about Bellman-Ford algorithm, which is kind of a replacement for the Dijkstra's algorithm. Now, Bellman-Ford algorithm is also a graph traversal algorithm, which is used to find the shortest path between particular source node and all other nodes in the weighted graph. The most beneficial feature of Bellman-Ford is that it can handle negative weight edges, unlike this task algorithm. Now let us look at the steps of Bellman-Ford. Pretty much alike to Distrast's algorithm, but it has some sense of where to change or where to fall apart, where it can fall apart. Uh, Initializing the distance of every vertex to be infinity, except source node set to zero. Uh, Repeating now. There is a process which has to be repeated n minus 1 times during the during this whole scenario, where this n minus 1 times is n, where n is particularly the total number of nodes in the graph given. So the process is for each edge group xy in the graph where x is the source node and y is the destination node, we keep relaxing the edges by updating the destination as we find the shortest path to that node. So basically, while traversing, you need to update the edges to the shortest path you can find. And thus, by traversing in only one particular direction, it becomes more efficient. It is calculated simply by finding the minimum of the current distance and the distance to you plus the weight of the edge. Now here, up to this point, this is as perfect as this star algorithm. But what if there is a negative weight included in the graph? So Bellman-Ford algorithm uses one more method, which is to traverse the whole graph and iterate itself once more to see if there are any negative weights in the graph, and if there are any negative weights, using them to find any shorter path if possible. This algorithm has a time complexity of big O of v times e, where v stands for the number of nodes and e is the number of edges in the graph, and it contains a space complexity of big O of v for storing the distance array. So thank you guys for listening up to me up to this point. Do check out our other videos to understand more about the A-star algorithm, particularly because we haven't yet understood anything about A-star algorithm, I suppose. And you already know about Dijkstra algorithm. So like the video and thank you.
Hello guys. Before I start my topic, I clarify that these videos are related to our discrete mathematics project, which is inspired by Professor Manish Kumar Gupta, Professor Manoj Rao, Professor Prasenjit Kundu, and our team members' names and IDs are shown on the screen. First of all, I will introduce myself. My name is Meet Deepak. My student ID is 20220123. So in this video, we cover what is the basic idea behind the A-star algorithm. So let's start it. In our daily life, we usually play games or use Google Map to find the best route related to our destination point. So to find the shortest path between any two nodes, A-star algorithm is very useful. So informally say that this algorithm is really a smart algorithm which separates it from other methods. The basic idea behind this algorithm is to explore the graph to consider both the actual cost and the estimated cost, where the actual cost is denoted as G value and the estimated cost is denoted as H value. The sum of these two values is used to determine the priority of nodes in the exploration process. And ESTA algorithm combines the concepts of Dijkstra's algorithm and greedy best first search algorithm. And this algorithm makes use of heuristic function, which is denoted as h of n, to estimate the cost of reaching the goal node from any node. And this heuristic function is the basically problem specific and should be admissible, meaning it never overestimates the actual cost. And our evaluation function, which is denoted as f of n, which is the sum of g of n and h of n, where g of n denoted as actual cost and the h of n denoted as estimated cost. The f of n indicates the priority of node. So ESTA algorithm and Dijkstra's algorithm are both popular graph traversal algorithms, but both have many differences like heuristic function, memory usage, optimality, exploration strategy, and many more. So to know more about what are the differences between ESTA algorithm and Dijkstra's algorithm, see you next video. I hope that you understand what is the basic idea behind the ESTA algorithm. So thanks for watching my video.
So hello, welcome guys. So as you know, we are doing a project on discrete mathematics. We are from DIICT. You can see here our team. So that's are our team members. And hello, myself is Meet Joshi. My ID is 2022001065. Okay. So our project is inspired by Professor Manish Kumar Gupta, Professor Manoj Raut, and Professor Prosejit Kundu. Okay, let's get further. So we are doing discrete mathematics project on algorithm behind Google Maps. Okay. So as you know, we are doing project on both algorithm, ESTA algorithm and Dijkstra algorithm. So today I will teach you about steps involved in ESTA algorithm. So let's get started. So in the first step, you want let's get assume that you want to go to the tea shop. Okay, tea shop from your home, which is the beginning location. Let's take this node beginning location start. Here is coffee shop, tea shop, your goal node. Okay, and then step 2, imagine there is a map with different nodes and roads with connecting them. So here we take start goal and goal node. So here take assume that a goal and there is b goal, which is a different nodes as described in step 2. So this is one way and this is one way. So there is one way S A G and there is another way S to B, B to G. It's S B G. Okay. So let's get further. Step 3 says you make a list of location to visit and starting with just your house. Like we either make list. Which is this? S A G and S B G. Okay. Step 4. A rough distance to the coffee shop or tea shop is indicated for the each nodes on the map. This estimated may be based on the journey time or the straight distance. Okay, so here describe that arrow S to A, you have to go S to A, then S A to G. So it get S A G and then S to B, B to G. It get S B G. Okay. Next, step 5, it says now you can calculate cost to reach every nodes. This price takes into account both the distance you have already traveled from your home and the estimated distance you will still have to travel to get to the coffee shop. Means like here we have given node C as start node, goal node says A and B. This is a path and we reach goal. So here we have actually here given we have estimated cost and in which on arrow we have actual cost to go to the S to A. Okay. Now step 6, making the nodes that is currently in use the node with the lowest overall cost. So you have formula in idea behind S algorithm. You have taught that formula is we have f of n is equal to g of n plus h of n, in which g of n is actual cost, h of n is estimated cost. I have described you here. You have estimated cost, here is actual cost. So if you calculate s to g, s to b, which is less, you will select because you have to reach fast. Next, step 7. So now if you have reached your destination, here coffee shop, yay, and you find your shortest path. But what if you didn't get, like I give you example, this is start node, this is let's say A, let's say is B, another one C, and then you reach goal node. Okay, so path S to A, and directly you reach as A to G, and then S to B, B to C, and C to G. Here what you do, you will calculate SA, G, and SBC, but you have another path. What if you calculate S, B, C, G? If it get lowest, you will select it. So you have to again start from S. Okay. Now step 9. Now see another nodes as I described you. If you have, we have taken C node, you figure out how much it will cost to get there from your starting point, your home, and if the distance is less, you update the cost. Like here I describe you. See, if here is lowest cost, you will select it, of course, because we have to reach fast. Now in step 10 says keeping in mind the parent node. Mean we have taken it parent node, we are starting from this node, that's why, and visit each nodes, you can keep track of the best path so far. So keep in mind what values occur and then go further. Now step 11. Now if you finish exploring to reach neighboring and current node, mark it as visited. Okay, that's simple. From step 6 to 11, keep going until either arrive at the coffee shop or run out of the nodes to investigate. Okay, so here you know I describe, go and check it. Now 13. Now let's you have again do step 6 to 11 or reach Kuros. You have discovered the quickest route because you have to come fast. Follow the parent notes from the coffee shop back to your house to determine the precise route. Okay, so enjoy your cup of tea, as our sir says. Yeah. Okay, now. Okay, I will give you a theory, basically idea, and with some normal example. But let's get one example. Here you have given say, and in which this is a red is what I have told you, it's estimated cost. And where is, okay, I color this, take color this is what actual cost. Okay, so as I described you, there is estimated cost which you can take its heuristic value as you have learned before. Now here is, you can see that, see, you have first, you will start from start node, this is a start node, and we have to reach where goal node. Let's assume this its estimated cost is 0, therefore by default. Okay, so now uh, we will start from S, so we can go to S to B or S to C. Okay, there is two path as you can see from diagram, and we have formula what, f of n is equal to g of n plus h of n, where g of n is, as you can see, g of n is actual cost described in purple, and there is a h of n which is estimated cost as you take it heuristic value which is on red pen. Okay, so now calculate s to b. Okay, so s to b we will select, so s to b there is actual cost 4 plus B's estimated cost is 12. So it takes 16. Okay. Now for S to C, we will take S to C, where S to C total is 3, which is actual cost plus C's estimated cost is 11. So it will take 14. So we have to keep in mind there is a 16 value we get and there is a 14 value we get. Okay. Now we reach S to B, S to C. Now for S to C, let's take S to C. We have completed. So S, C, and we can go further to E and S, C to D. Okay. So let's get. So now S to C. Okay. So S to C, and where we are going E. So here you see 3 and 10. Okay. So 3 plus 10, 13, which will actual cost. And then for E, there is estimated cost is 4. So we'll plus 4. What we will get? 17. Keep in mind. Okay. And for SC to D, again S to C is 3 actual cost and C to D is 7 actual cost. Okay. So 3 plus 7 is 10. And plus estimated cost of D is 6. So we will get value is 16. Okay. Now as we go through the SC, now let's take SB. From S to B, we can go SB to F and SB to E. Okay, let's SB to F and SB to E. Okay, done. So now SB to B to F. Take this part. So S to B, B to F, as you see in diagram, actual cost will be 9. And then estimated cost of F is 11. So what you will get? 20. Keep in mind. And then for SB to E. So S to B is 4 actual cost. And then B to E is 12 actual cost. Okay. So the actual cost will be 16. And then estimated value of E is what? 4. So we will get again 20. Keep in mind. Okay. So further, now as you can see here we have 17, 16, 20. We will take less value. So less value is SC to D. Let's keep in mind SC to D. Okay. Now SC, D, and we will go through E. Okay. So what will be SC to S to C 3, C to D 7 and D to E 2. So actual cost will be 3 plus 7 10 plus 2 12. And then estimated value of E is 4. So it will get 16. Okay. So again 16 less than this 17, 60, 20, 20 again 16. So we will keep in mind. Now it will reach us to F. Sorry, G, which is our goal node. Okay. So we will reach. So now let's take S to C 3, C to D 7, D to E 2 and E to G 5. So 3 plus 7 10, 10 plus 2 12, 12 plus 5 17. Okay. Plus actual cost of estimated cost of G is 0. So we will get 17. So here is our answer. We will get 17 as a goal node. And now let's see. What if we take path S, B, F to G? Because SBF also we will get goal node. Let's take what we will get value. So S to B, B to F, 4 plus 5 plus 16. What is 25? Actual cost and plus estimated cost G is 0. So we will get 25. So it is very high. We will have to take less. So 17 is our answer. This value we will get. So the right path is S C, C to D, D to E and E to G. Okay. So like this you will get your best path from A-star algorithm. Okay. Next slide. Okay. So thank you. Hope you understand it very clearly. Okay. So bye. Hello guys. So I am me Josie. I am from DICT. As you know, we are doing a discrete mathematics project on algorithm behind Google Maps. So the project is inspired by Professor Manish Kumar Gupta, Manoj Raut, and Prosenjit Kundu. So here is our team, as you can see. And I am Meet Joshi, and this is my ID 20220106. So today I will explain you difference between Dijkstra algorithm and A-star algorithm. So as you already know that you already understand introductory part of both algorithm, idea behind both algorithm, and steps involved in it. You can have roughly sketch in your mind about how can both algorithm change from each other. So let's find out what is the difference between both algorithm. So this is A-star algorithm is more preferred due to its completeness, optimality, and optimal efficiency. As you know, A-star algorithm is similar to Dijkstra's algorithm and uses a heuristic function, okay, to navigate a better and more efficient path. Unlike Dijkstra's, the A-star algorithm focuses on only the destination nodes and not the others. Thus, this algorithm proves to be more proficient, and A-star algorithm confirms to give optimal solution, while there is exception in Dijkstra's algorithm for negative weight values, as you know. A-star also takes parameters such as time requirement, distance, etc., optimizing and choosing the better nodes. Okay, so now I categorize in four ways. Approach is heuristic function, memory usage, and optimality for finding difference between both algorithm. So let's get further. So here is come approach method. Okay. So see here in Dijkstra's algorithm, mainly this greedy algorithm which starts its calculation from the source node and iteratively explores the neighboring nodes. After approaching all nodes, basically it's updating the distance. This process will continue until it reaches the final destination node or until explored every reachable nodes. As you know, you have both steps involved in Dijkstra's algorithm. You know this points. For A-star algorithm, as you know, it is also a heuristic search algorithm that uses both the actual cost from the start node G value and an estimated cost to the goal node H value to make decision about which node to explore next. You know the formula for A-star algorithm? It's f of n is equal to g of n plus h of n, in which h of n is estimated cost, and g of n is actual cost, so you can relate with it. So let's get further. Second point, it's heuristic function. So basically in it, Dijkstra's algorithm, it does not use any heuristic function, you know. It only considers the actual cost from the source node to each node, in which you know only you have source node's value, but another nodes from source node you basically it consider as initialize infinite. And for A-star algorithm, this algorithm uses heuristic functions that estimated the cost from a node to the goal node. As using this heuristic function in this algorithm affect the performance and optimality of the algorithm. So let's get further. In memory usage part, Dijkstra's algorithm, as it requires a priority queue, okay, or a mine heap, and requires priority queue to keep track of the nodes to be explored. Function of growing the size of the priority queue is significantly in dense graph, leading to higher and memory usage. Okay. And for A-star algorithm, however, compared to Dijkstra's approach, the memory usage can be decreased by employing the right heuristic function, because it uses the heuristic function. Next, for optimality. So optimality for Dijkstra's algorithm, it ensures that the shortest route between the source node and all other reachable nodes in the graph will be discovered. It may, however, investigate paths that are ineffective for getting to the destination beacon. It does not take into consideration any information about the objective nodes. Here you see ineffective for getting to the destination. I will watch one YouTube video in next slide to understand it. And now, a star algorithm given a valid heuristic function. It ensures that the shortest route between the source and goal node will be found. When compared to Dijkstra's algorithm, the A-star method generally finds the optimal path more quickly since it takes into account both actual cost and the predicted cost to the target H value. Okay, as you know from formula. So let's watch this video. As I know you in approach in optimality math part, difference between both is also described in this YouTube video. Let's get more. So see here, left side it's A star algorithm and right side is Dijkstra's algorithm. So see here, A star is directly and Dijkstra is approaching all nodes. See here, Dijkstra is approaching every nodes and taking more time. Okay, now we will take one more example. Okay, so I hope you will understand it very great. So thank you. Bye.
Hi friends, we are from DAIICT. Our group is making a project on algorithms behind Google Maps. In this video, we will cover two topics. Heuristic function, which will be covered by Mihir Patel 2022015006, and admissibility of A-star algorithm, which will be covered by Smith Pfeffer 2022012553. Hi friends, I am Mihir Patel. Heuristic function. A heuristic function, also known as a heuristic evolution function or simply a heuristic, is a function used in artificial intelligence and optimization algorithms to estimate the quality or potential of a solution without necessarily guaranteeing the optimal solution. It provides an informed estimate or guidance to the algorithm, helping it make a decision and prioritize certain actions. The purpose of a heuristic function is to guide the search process towards a more promising solution by assigning a scores or values to different states or configuration. These scores are typically based on domain-specific knowledge, problem constraints, or heuristic derived from past experience. The algorithm can then use these scores to evaluate and compare different options and choose most promising ones. Heuristic functions are commonly used in various algorithms, such as heuristic search algorithms, example A-star algorithm, evolutionary algorithms, and local search algorithms. They play a crucial role in problems where finding the optimal solution is computationally expensive or intractable, allowing for a more efficient exploration of the search space. It is important to note that heuristic functions are not guaranteed to provide the optimal solution, but they aim to guide the algorithm towards a good solution in a reasonable amount of time. The quality of the heuristic function greatly affects the performance and effectiveness of the algorithm it is used in. Designing effective heuristic functions require deep understanding of the problem domain and the ability to capture relevant information to guide the search process effectively. Thank you.
Hello friends. So some points related to heuristic function is already taught by Mihir Patel and the remaining part will be covered by me. And what will I say in this video I already wrote in the slides. So it's easy to understand. So let's start. In computer science, the heuristic function h of n is referred to as acceptable and it is always less than or equal to the actual cost, which is the true cost from the present point in the path. H of n is never bigger than h star n in this context. This has to do with the idea of reliable heuristics. All reliable heuristics can be used. However, not all reliable heuristics can be used. The cost of reaching the goal state is assessed using an admissible heuristic in an informed search algorithm. However, if we need to discover a solution to the problem, the estimated cost must be lower than or equal to the true cost of reaching the goal state. The algorithm employs the allowable heuristic to determine the best estimated route from the current node to the objective state. So let's see the evolution function in NESTA algorithm. The evolution function f of n is the sum of g of n and h of n, where the n is the current node, f of n is the evolution function, g of n is the cost from the initial node to the current node, and h of n is the estimated cost from the current node to the goal state. So let's see some conditions about heuristic functions. When h of n is less than or equal to h star n, it is called underestimation, and the h of n is greater than or equal to h star n, it is called overestimation. At last, we see some key points. The heuristic function h of n is admissible if h of n is never larger than h star n, or if h of n is always less than or equal to the true value. If h star employs an admissible heuristic and h of core is equal to 0, then we can argue that a star is admissible. If the heuristic function is constantly turned to be low with respect to the true cost, then you are going to get an optimal solution of 100%. I hope that you understand this topic. Thanks for watching this video.
Algorithm pseudocode and complexity. First up, we have the pseudocode. Now, first of all, we have certain number of vertices. We need to add all of them into a set called Q. We initialize all the distances of these vertices to infinite and the previous of these vertices to undefined. and we add all these vertices to the set Q. Okay, now we initialize the distance of source to 0. While Q is not empty, U is the vertex in Q with minimum distance. It is nothing but initially it is nothing but U. Initially is nothing but the source. We remove this U from Q and we find all the neighbors of this particular vertex with the least cost. Once we have found out the neighbors, we'll find out their cost. How? By adding the cost of this node with the least cost plus the distance or the cost between this node and its particular neighbor node. If this new found out cost, which is alt over here, is less than the cost which we already have for this node in Q. Initially, it will be infinite, but there might be cases when we find out the cost of a particular node twice or thrice. So, in those cases, if the newly found node cost, if the newly found cost is less than the existing cost for this particular node, then we update the cost of this node and also update the previous of this node to U. And we return the distance in previous. Again, we go back to Q. We find out the node with the least cost. Then we find out its neighbors. Then we find out the cost of all of its neighbors. If the newly found cost is less than the existing cost, we update it. Else, again, we go back to Q. We find the node with the least cost, find its adjacent nodes, and so on. The process goes on till we find the target node. Once we found the least cost, the target node, our mission or our target is achieved. We have found out the shortest path between the source node and the target node. Next up, we have the time complexity. Now, the time complexity is big of E log V. Why? The reason is that if we have to store we have to insert V vertices in the set Q. So it takes big of V time. Next, we have to calculate the shortest distance, which node has the shortest path in Q, which takes log of V time. And since we have to do it for each vertex, we multiply it by V. Next, once we found out the node of the least cost, we have to also find out the cost of its neighbors. More the edges, more the neighbors, because the neighbors are attached to this particular node through edges. To find out the respective cost of vertices, and again to update the cost in Q, it takes log of V time. And since the number of neighbors is equal to number of edges from that particular node, we multiply it by E. So now we have three things: big of V log V, big of E log V, and big of V. And out of these three, big of E log V is biggest. Thus, the time complexity is big of E log V. Next, we have space complexity. We need big of V space for storing the set of V elements and big of V for storing vertices. So space complexity is big of V. Next, I'll talk about A-star algorithm pseudocode and complexity. First of all, the pseudocode. Now, the pseudocode is divided into many steps. First of all, initialize the open list and closed list. Open list is a set of all nodes whose cost has been identified, but we are not yet sure whether it is the shortest path or not to that particular node. And closed list is a set of all nodes whose shortest path is already found out. Okay. Next, while the open list is not empty, while there are some nodes, we find out the node with the least f. Pop off this particular node from the open list, and put it into closed list. Why? Because we found out the shortest path with this node. Next, we generate all the skew successors or the neighboring nodes. Now, for each successor, if the successor is the goal, we stop the search. But if it's not, we find out its cost. How? By adding two values, G and H, where H is the heuristic value and G is the value from the source node to the particular node. Once you have added up, now again we check. We check if the node was already present in the open list, and we compare that value to our new value. If our new value is less, then we update the cost of that node in the open list, else we skip this node or the successor. Again, we check in closed list. In closed list, if our a new value is less than the existing value in the closed list for that particular node, then we add it to the open list, else we skip the successor. The for loop. When the for loop will end, it means that we have evaluated the shortest path to each of the neighboring nodes. Next, it will push this element q, which has the shortest path, to the closed list, and this will continue until there are nodes present in the set q. So again, we'll go back to q, we'll find the node with the shortest path, we'll find its neighboring nodes, we'll find the cost of the neighboring nodes, we'll compare it in the open list, in the closed list, and thus after that we'll add the node q to the closed list. Why? Because all its neighboring nodes paths has been evaluated, the shortest path has been evaluated, so we can add the node q to the closed list, and this will end the while loop. Now the while loop will continue until q is empty, or if we have reached the target node. Once we have reached the target node, which means we have found out the shortest distance to it, and thus we have achieved our target. Next, moving towards the time complexity. The time complexity of A star depends upon the branching factor. We can visualize A star algorithm as a tree. If there are more branches, then naturally the time taken to reach the target will be more. Also, it depends on the depth of the target node. If the target node has a good depth, then naturally more time will be taken to reach the node. Thus, the time complexity is big of p raised to d. Next, we'll talk about space complexity. Now, the space required is to store the closed list, open list, and the nodes. Thus, the space complexity is big of V, where V is the number of vertices.
Hello guys, I am a student of DAIICT and currently we are working on a project in discrete mathematics that is inspired by our respected professors, Professor Manish Kumar Gupta, Professor Manoj Rao, and Professor Prosenjit Kundu. This is our team, and there are 6 members in our team. I am Dishant Patel, and my student ID is 202201260. As you know, if you have watched the previous videos, then you have idea that we are working on the algorithms behind Google Map, how Google Maps uh, use Dijkstra and A-star algorithm to navigate us and find the most cost efficient way, and it helps us a lot. Then in this video I am explaining an example of A-star algorithm. So let's start the example. In this example, we have a source node and only one goal node. Why I am saying that we have only one goal node? We have already seen in Dijkstra's algorithm that there was one source node and all the other nodes were goal nodes. But here there is only one goal node. That is the major difference between Dijkstra's algorithm and A-star algorithm, and all these remaining nodes are intermediate nodes. Okay. We have also learned that the cost to reach a node is denoted by f of n and is equal to the sum of g of n and h of n. Here g of n is actual value to reach that node from source node. And h of n is heuristic function. Heuristic function means an estimated value that is an estimation value to reach the goal node from that node. Okay. So firstly, we are now starting our example, and firstly we will find f of s. So f of s is equal to g of s plus h of s. So as we know, g of s is 0 because the cost to reach the source node from the source node is 0, obviously, and the heuristic value here, all these purple colored value is heuristic values of that node, particular node. So the heuristic value of this source node is 14, so I have written it here. So f of s will become 14. Okay. So now starting with the source node, as we have two different paths, S to A and S to B. Okay. Now we will find f of A, yes, and f of B. F of A is g of A. What is the actual value that requires to reach to the node A? That is 4. And what is the estimated value, heuristic value? That is 12. So f of A equal to 4 plus 12, that is 16. And f of B similarly, g of b is 3 and the heuristic value of b, that is 11. So f of b will become 14. Okay. So here f of b is less than f of a. Okay. So we will choose this path for our further traversing s to b path. Okay. Okay. So further we have two more paths, S to B and B to D, and S to B and B to C. Okay. So now f of C. So f of C equal to g of C, and what is the value of g of C? This 3 plus this 7, actual value, that is 10. So f of C is 10 here, no? Okay, here is a mistake. F of C is here. This is f of D. Okay, first is f of D. Is not this. First is f of D. This is 3 plus 10, 13, plus heuristic value of D is 4. So f of D is equal to 17, and f here is f of C. Actual value of f of C, g of C is 10, and heuristic value is 6. So here 16, I have written 16. Here f of C is less than f of D. Okay, here f of C is less than f of D. So it is obvious that we will choose S to B path and B to C path. Okay, but remember the value of f of A. It was also 16. So we have now two possibilities. If we are going to S to B and then go to B to C, or either we can go to S to A directly. So first possibility, along the path S to A. Along the path S to A, we have two further paths, S to A and A to E, and S to A to D. So F of D along the path S to A and A to D, the value of D is, actual value will become 4 plus 12, 16, and the heuristic value of D is 4. So f of D will become 20, and f of E is actual value is 4 plus 5, 9. and the heuristic value is 11. Okay, so f of e will become 20. And the other possibility that we have is along the path S to B and B to C. Okay, so now we are at this node C, and we can only go to the node D. Okay, so we will find f of D along this path S to B and B to C path. Okay, so f of D value will become 3 plus 7 plus 2 is the actual cost, and 4 is the heuristic value. So actual cost is 12, and the heuristic value is 4. So f of d will become 16. Now all the three possibilities from all these three possibilities, we get 16 from this path, and from the first possibility we got two values, 20 and 20. So we have minimum value 16, so we will keep moving on this path. Okay, now from node D we can directly approach to the goal node. So the value of the goal node f of g will become 17 as 3 plus 7 plus 2 plus 5. Okay, and the heuristic value of this goal node is obviously 0, as the actual value of this source node is 0. Similar, so f of g will become 17. Okay, and we have reached the goal node with the minimum possible cost. Here we have completed our example, but what? But have you observed in this example all these heuristic values are less than the actual values that are required to reach the goal node from that node. See, here it is 14, and that what is actual cost? 4 plus 5 9 plus 16 25. Okay, so you can check all these values that are perfectly less than the actual values. So why we have to do this? So if we choose these less values from the actual values, we can get optimal solution for to reach this goal node. Okay, it is called this condition is called underestimation. Underestimation. There are two conditions: underestimation and overestimation. If we choose the condition of underestimation, we find the optimal and the best cost efficient route to reach the goal node. Okay, and so this shows the admissibility of this A star algorithm. Okay, so I hope you have understand this example very well, and all these topic that we have learned, that we have taught you, and so that's all from my side. Thank you for watching this video. This was the last video, so bye. Thank you for your support. Thank you very much.